Beyond the familiar orbits of planets like Neptune, there's a hidden realm of ice, darkness, and mystery stretching so far into space that it defies human imagination. Picture a vast cosmic graveyard where chunks of primordial ice and rock drift silently, untouched by sunlight for billions of years. This is the Kuiper Belt, a donut-shaped ring of frozen worlds, and beyond it the Oort cloud, a distant, ghostly shell of icy bodies so remote that even our most powerful telescopes struggle to glimpse them. Together, they form the solar system's final frontier, a place where the story of our cosmic neighborhood remains half-written, waiting to be unraveled. What secrets do these frozen wastelands hold? Could they be the key to understanding how our solar system was born, or even where Earth's water and the ingredients for life first came from? Out here, temperatures plunge so low that gases freeze solid, and the faint warmth of the sun is nothing more than a distant memory. Yet within this icy darkness lie clues to our past and perhaps even our future. Some of these objects are time capsules, preserving materials from the dawn of the solar system, while others might one day become stepping stones for humanity's expansion into the stars. This is a journey to the edge of everything we know, where dwarf planets like Pluto and Eris wander among millions of unseen siblings, and where comets are born before streaking toward the inner solar system in blazing displays. Over the next few minutes, we'll explore what makes these distant realms so fascinating, from the strange, tumbling orbits of Kuiper Belt objects to the mind-bending scale of the Oort cloud, a place so vast it could hold trillions of icy bodies. Strap in, because we're about to venture into the solar system's frozen frontier, where the mysteries are as deep as space itself. The Kuiper Belt is like a cosmic junkyard at the edge of our solar system, a vast collection of icy leftovers from its earliest days. Think of it as a frozen archive preserving remnants of the swirling disk of dust and gas that once birthed the planets. Officially beginning just past Neptune's orbit, this region stretches outward for billions of miles, filled with objects so ancient and untouched that studying them is like peering into a 4.5 billion-year-old time capsule. For decades, astronomers suspected something was out there. As far back as the 1940s, scientist Gerard Kuiper theorized that a belt of small, icy bodies might exist beyond Neptune, though he thought it would have been cleared away by planetary gravity. His ideas planted the seed, but it wasn't until 1992 that technology caught up with theory. That's when astronomers David Jewett and Jane Liu spotted the first confirmed Kuiper Belt object, a tiny frozen world they named Albion. This discovery opened the floodgates. Suddenly, what was once speculation became undeniable fact. The Kuiper Belt was real, and it was teeming with frozen wanderers. Many of these objects, like Pluto, are large enough to be considered dwarf planets, while others are smaller than a city block, but their importance is enormous. Each one holds chemical fingerprints from the solar system's infancy, offering clues about how planets form and even how Earth got its water. The Kuiper Belt isn't just a relic of the past, though. It's also surprisingly active. Some of these distant objects have moons, thin atmospheres, or even hints of hidden oceans beneath their icy shells. And because they're so far from the sun, their slow, tumbling orbits preserve conditions that have remained unchanged for eons. Every new mission, like NASA's A New Horizons flight past Pluto and Arrokoth, peels back another layer of mystery, showing us just how much we still have to learn about this frozen frontier. But if the Kuiper Belt feels remote, the Oort cloud is almost unimaginable, a ghostly sphere of ice stretching so far into space that it marks the true boundary of our sun's influence. While the Kuiper Belt orbits in a relatively flat disk, the Oort cloud forms a vast three-dimensional shell around the entire solar system, beginning roughly 2,000 times farther from the sun than Earth and stretching outward for light years. This isn't just the edge of the planetary neighborhood. It's the frontier where the sun's gravity finally loses its grip and interstellar space begins. The Oort cloud exists mostly in theory, a concept proposed by Dutch astronomer Jan Oort in 1950 to solve a cosmic mystery. Where do long-period comets come from? These icy visitors, like Halley's Comet, swing by Earth only once every few centuries or even millennia, tracing elongated orbits that can't be explained by the Kuiper Belt alone. Oort realized there must be a distant reservoir of icy bodies, a place where gravitational nudges from passing stars or galactic tides could occasionally send these frozen wanderers hurtling inward. What makes the Oort cloud so fascinating is its scale and its elusiveness. Unlike the Kuiper Belt, where we've catalogued thousands of objects, no telescope has ever directly observed an Oort cloud object. The distances are simply too vast and the sunlight too faint. Yet astronomers are confident it's there, a cosmic freezer holding perhaps trillions of icy fragments, some as large as mountains, left over from the solar system's chaotic infancy. Imagine a place where temperatures hover just a few degrees above absolute zero, where a single orbit around the sun can take millions of years, and where the nearest star's gravity matters almost as much as our own sun's. This is the Oort cloud, a place so distant that human-made probes like Voyager 1 won't reach its inner edge for another 300 years. And yet, despite its remoteness, it may hold answers to questions we haven't even thought to ask. Some theories suggest the Oort cloud could be a cosmic scrapbook containing not just relics from our solar system's formation, but also captured interstellar visitors, icy bodies stolen from other stars as they drifted by. Others speculate that interactions with passing stars might have reshaped its structure over billions of years, leaving behind clues about the sun's journey through the galaxy. Even more tantalizing is the possibility that objects from the Oort cloud delivered water and organic molecules to Earth long ago, seeding the ingredients for life during our planet's fiery youth. For now, the Oort cloud remains one of astronomy's great unsolved puzzles, a realm we understand mostly through mathematical models and the rare comets that venture inward. But with every new discovery, we peel back another layer of its mystery, inching closer to understanding how this frozen halo connects us to the wider cosmos. The Kuiper Belt and the Oort cloud might both be icy realms at the solar system's edge, but they're as different as a bustling city and a ghost town. Picture the Kuiper Belt as a relatively compact, bustling neighborhood just beyond Neptune, a flat, disk-like region filled with thousands of known objects, some as large as Pluto, others no bigger than a refrigerator. It's close enough that sunlight, though weak, still faintly illuminates these frozen worlds. By contrast, the Oort cloud is more like a sprawling, invisible fortress, a vast spherical shell so distant that the sun appears as just another bright star. If you could stand on an Oort cloud object, you'd need a telescope just to spot the inner solar system. Distance alone isn't the only difference. The Kuiper Belt is packed with rocky ice mixtures, remnants of the early solar system that never grew into full planets. These objects orbit in predictable, flat paths, much like the planets do. The Oort cloud, on the other hand, is a chaotic jumble of icy fragments, some of which may have been flung outward by the gravity of giant planets long ago. Their orbits are so stretched and tilted that they resemble wild, looping roller coasters compared to the orderly circuits of the Kuiper Belt. Composition tells another tale. Kuiper Belt objects often contain methane, ammonia, and water ice, frozen relics of the solar system's infancy. Some even have thin atmospheres when they swing closer to the sun. The Oort cloud, though, is so cold and untouched that its ice might be purer, preserving primordial materials almost unchanged for billions of years. There's even a chance it harbors interstellar interlopers, icy visitors captured from other star systems, making it a cosmic museum of not just our history but the galaxy's. Scale is where the mind truly reels. The Kuiper Belt stretches from about 30 to 55 astronomical units from the sun. That's 30 to 55 times Earth's distance. The Oort cloud begins roughly 2,000 astronomical units out and may extend over 100,000, reaching almost a quarter of the way to the next star. To visualize this, imagine the entire inner solar system, from Mercury to the Kuiper Belt, as a golf ball. The Oort cloud would be a diffuse cloud of dust surrounding it, stretching across a football field. Even their origins might differ. The Kuiper Belt likely formed in place, a leftover construction zone from the solar system's birth. The Oort cloud, however, could be a cosmic refugee camp, its objects scattered outward by the gravitational chaos of young gas giants, then shaped over eons by the gentle tugs of passing stars and galactic tides. This makes it a time capsule not just of our solar system's youth, but of its dynamic journey through the Milky Way. Yet for all their differences, these two realms are deeply connected. Comets from the Kuiper Belt, like Halley's, visit us every few decades, while Oort cloud comets may take millennia or longer. Together, they remind us that the solar system isn't just the planets we know, but a vast, layered ecosystem of ice and rock, each zone telling its own piece of an epic story. Pluto wasn't just demoted, it became the crown jewel of an entirely new cosmic neighborhood. Once considered the 9th planet, this tiny world's reclassification as a Kuiper Belt object in 2006 didn't diminish its importance. It revealed just how much we had underestimated the icy frontier beyond Neptune. Pluto's story is a gateway to understanding the Kuiper Belt's secrets, proving that sometimes losing planetary status means gaining a far more intriguing identity. When NASA New Horizons spacecraft finally reached Pluto in July 2015 after a 9-year journey, it shattered every expectation. Instead of a barren, cratered ice ball, the probe revealed a world of staggering complexity, towering mountains of water ice, glaciers of frozen nitrogen, and even hints of a subsurface ocean. But perhaps the most striking discovery was Pluto's heart-shaped plain, Sputnik Planitia, a vast basin filled with slowly churning glaciers that reshaped the landscape like a cosmic lava lamp. These features suggested something astonishing. Pluto isn't just a frozen relic, it's geologically alive. The mission also unveiled Pluto's thin but dynamic atmosphere, where nitrogen snow falls and sunlight breaks apart methane to create hazy layers of organic compounds. These discoveries forced scientists to rethink how small, distant worlds can retain enough heat for such activity. The answer might lie in radioactive elements deep in Pluto's core or tidal interactions with its largest moon, Charon, a binary partner so massive that the two orbit a shared point in space like a pair of figure skaters holding hands. New Horizons didn't stop at Pluto. 3.5 years later, it raced past Arrokoth, a bizarre, two-lobed Kuiper Belt object resembling a flattened snowman. This primordial fossil, untouched by planetary collisions, offered a pristine snapshot of the building blocks that formed planets like Earth. Its smooth surface and gentle merger of two smaller bodies supported theories that planet formation began with slow, gentle collisions in the early solar system's icy outskirts. Pluto's demotion turned out to be a scientific blessing. By reclassifying it, astronomers didn't just redefine a world. They unlocked a new category of celestial objects, each holding clues to our solar system's wild youth. The more we learn about Pluto and its Kuiper Belt neighbors, the clearer it becomes. This distant realm isn't the end of the solar system's story. It's a vibrant, dynamic chapter we're only beginning to read. Pluto may be the most famous resident of the Kuiper Belt, but it's far from alone. Beyond its orbit lies a menagerie of strange, icy worlds, each with its own secrets and surprises. Take Eris, for example. Discovered in 2005, this distant object ignited a firestorm in astronomy because it's actually more massive than Pluto. Its detection forced scientists to confront an uncomfortable truth. If Pluto was a planet, then Eris had to be one too, along with countless other objects waiting to be found. Eris isn't just Pluto's rival, it's a world of extremes. Despite being smaller in diameter, its greater mass suggests a rockier core beneath its icy shell. It orbits the Sun at such a steep angle that it plunges far above and below the flat plane of the solar system, tracing a path more like a comet than a planet. Even its surface tells a story of cosmic violence coated in reflective methane ice, so bright it's one of the most luminous objects in the solar system, likely the result of ancient impacts churning up fresh ice from below. Then there's Haumea, a world so bizarre it defies simple explanation. Shaped like a squashed football, this rapidly spinning dwarf planet completes a full rotation every 4 hours, flinging material outward to form 2 small moons and a faint ring system, something never before seen around objects this small. Scientists suspect Haumea's odd shape comes from a cataclysmic collision billions of years ago, a crash so violent it turned the dwarf planet into a tumbling cosmic top. Makemake, named after the creation deity of the Rapa Nui people, hides its own mysteries. This reddish-brown world lacks a measurable atmosphere, yet telescope observations suggest patches of frozen methane and possibly even ethane littering its surface. What makes Makemake particularly intriguing is its brightness variation. Some regions reflect far more sunlight than others, hinting at complex geology beneath its frozen exterior. The discovery of these worlds didn't just challenge Pluto's status, it revolutionized our understanding of the solar system's architecture. Suddenly, the Kuiper Belt wasn't just a repository of icy leftovers, it was a dynamic region with its own distinct classes of objects. Some, like Pluto and Eris, are large enough to pull themselves into round shapes through gravity. Others, like Haumea, bear the scars of ancient violence. And then there are the classical Kuiper Belt objects, orbiting in nearly circular paths untouched by Neptune's gravity, preserving clues about the solar system's original structure. These distant worlds also forced astronomers to rethink what makes a planet. The International Astronomical Union's 2006 decision to redefine planets, requiring them to clear their orbit of other large bodies, wasn't just about Pluto. It acknowledged that our cosmic neighborhood contains not just 8 major planets, but an entire spectrum of fascinating worlds, each with its own story to tell. The Kuiper Belt isn't just Pluto's backyard, it's a vibrant, diverse frontier we've only begun to explore. Every new observation peels back another layer of mystery. Why do some of these objects have moons while others don't? How did Haumea's rings form? Could subsurface oceans exist on worlds so far from the Sun? Each question reminds us that the Kuiper Belt isn't a static relic. It's a living laboratory where the processes that built our solar system are still playing out in slow motion. And with missions like New Horizons and next-generation telescopes coming online, we're on the verge of uncovering even more surprises from this frozen, far-flung realm. The Kuiper Belt isn't just a collection of frozen leftovers, it's a frozen blueprint of our solar system's chaotic beginnings. To understand how this distant region came to be, we need to rewind time over 4.5 billion years, back to when the Sun was a newborn star surrounded by a swirling disk of gas and dust. This protoplanetary disk was the construction site for everything we see today, from rocky planets like Earth to gas giants like Jupiter. But while most of that material clumped together to form worlds, some of it never made the cut. The Kuiper Belt is what remained the spare parts of planetary construction, frozen in place at the edge of the solar system. One leading theory suggests the Kuiper Belt formed when the gravitational pull of Neptune sculpted the outer solar system. As the giant planet migrated outward in its youth, its gravity acted like a cosmic snowplow, pushing smaller icy bodies ahead of it. Some were flung into distant orbits, while others collided and merged, creating the diverse objects we see today. This explains why the Kuiper Belt isn't a uniform ring but a dynamic zone with distinct populations, some objects locked in stable orbits, others influenced by Neptune's gravity in complex ways. The real treasure of the Kuiper Belt lies in its planetesimals, the building blocks of planets. These ancient chunks of ice and rock never grew large enough to become full-fledged worlds, but they offer a snapshot of the solar system's raw materials. Imagine them as cosmic fossils, preserving the same mixture of water, ammonia, and organic compounds that once swirled around the infant sun. When NASA's New Horizons mission visited Arrokoth, it found a pristine, unaltered relic from this era, a pair of gently merged lobes showing no signs of violent collisions. This suggests planetesimals didn't just smash together chaotically, but grew through slow, gentle encounters in the solar system's frigid outskirts. But the Kuiper Belt story isn't just about what stayed behind, it's also about what was kicked out. Computer simulations reveal that during the solar system's early turmoil, Jupiter and Saturn's gravity likely hurled countless icy bodies into distant orbits, contributing to the Oort cloud's formation. This makes the Kuiper Belt a kind of cosmic borderland, caught between the orderly planetary zone and the scattered wilderness beyond. Its structure part preserved relic, part scattered debris holds clues to the gravitational battles that shaped our entire neighborhood. What's fascinating is how much these distant ice worlds can tell us about Earth's own origins. Some scientists believe Kuiper Belt objects delivered water and organic molecules to our planet during the late heavy bombardment, a period around 4 billion years ago when the inner solar system was pummeled by icy projectiles. If true, the same frozen bodies drifting silently beyond Neptune might have played a crucial role in making Earth habitable. The Kuiper Belt also challenges our assumptions about how planetary systems evolve. In other star systems, astronomers have spotted similar debris disks around young stars, suggesting these icy zones might be universal features of planet formation. By studying our own, we're not just uncovering local history, we're piecing together a blueprint for how planets emerge across the cosmos. Every mission, every telescope observation adds another piece to this puzzle. From the discovery of binary Kuiper Belt objects pairs locked in delicate gravitational dances to the detection of exotic ices like nitrogen and methane on their surfaces, each finding reshapes our understanding of the solar system's infancy. The Kuiper Belt isn't just a distant curiosity, it's a time machine preserving the conditions of a vanished era when the planets were still taking shape. And as we explore further, we might find that its icy realms hold even deeper secrets about where we all came from. The Oort cloud's existence is one of the solar system's greatest puzzles, not just because of its mind-bending distance, but because its very origins defy easy explanation. Unlike the Kuiper Belt, which formed relatively close to where it sits today, the Oort cloud is a cosmic refugee camp, its scattered inhabitants likely ejected from the inner solar system during a period of violent upheaval billions of years ago. Picture the early solar system as a chaotic construction zone where newborn planets jostled for position, their immense gravity hurling icy debris outward like pebbles from a spinning tire. This gravitational pinball might explain how objects born near Saturn or Jupiter ended up in a distant shell trillions of miles away. One leading theory points the finger at the gas giants, particularly Jupiter and Saturn, whose gravitational might could have acted like a cosmic slingshot. As these planets migrated through the young solar system, their gravity would have destabilized countless smaller bodies, some flung sunward to become comets, others ejected to the fringes. Computer simulations show this scattering could have populated the Oort cloud in just a few 100 million years, a blink of an eye in cosmic terms. But there's a twist. Not all Oort cloud objects may have originated in our solar system. Some could be interstellar hitchhikers captured by the sun's gravity as it passed through dense molecular clouds early in its history. Another clue comes from the cloud's spherical shape, which stands in stark contrast to the flat disk of the Kuiper Belt. This suggests the Oort cloud wasn't gently assembled but violently sculpted. its objects' orbits randomized by gravitational chaos. Even passing stars may have played a role during the Sun's infancy, when it was still nestled in its birth cluster. Close encounters with sibling stars could have yanked icy bodies into extreme orbits. Over eons, the gentle tug of the Milky Way's tidal forces further shaped this distant halo, stretching some orbits into the immense loops we see today in long-period comets. Yet the Oort cloud isn't just a relic of destruction, it's also a time capsule. Some of its most primitive objects might contain ices that have never been exposed to significant heat, preserving molecules unchanged since the solar system's birth. Others could hold isotopic ratios hinting at the Sun's formation environment, or even organic compounds similar to those that seeded life on Earth. What makes this region so tantalizing is that its formation story isn't just about our past, it's a window into how star systems everywhere evolve. Exoplanet discoveries reveal that giant planet migrations are common, meaning Oort cloud-like structures could surround countless stars. By decoding our own, we're glimpsing a universal process, the gravitational ballet that turns chaotic debris into orderly systems, with frozen remnants lingering at the edge like cosmic breadcrumbs. Every long-period comet that streaks through the inner solar system is a messenger from this frontier, offering fleeting clues about the Oort cloud's composition and history. Missions like the upcoming Comet Interceptor aim to study one such visitor up close, potentially revealing whether these icy nomads truly are pristine time capsules or battered survivors of a turbulent youth. Until then, this distant cloud remains a shadowy enigma, a testament to the solar system's violent beginnings and a reminder that even the emptiest reaches of space hold stories waiting to be told. Comets are the solar system's ancient wanderers, icy time capsules that occasionally streak into our skies with glowing tails, each one a messenger from the frozen fringes of our cosmic neighborhood. But not all comets are the same. Some, like Halley's Comet, return like clockwork every few decades, while others, like the dazzling Hale-Bopp, appear without warning and vanish for millennia. This split between short-period and long-period comets isn't random, it's a direct reflection of their origins in two vastly different regions, the Kuiper Belt and the Oort cloud. Short-period comets, those with orbits lasting less than 200 years, are essentially cosmic locals, hailing from the Kuiper Belt just beyond Neptune. These icy bodies are nudged inward by gravitational interactions, often with Neptune itself, sending them on elliptical journeys toward the Sun. When they get close enough, solar heat vaporizes their frozen surfaces, creating the iconic glowing comas and tails we see from Earth. Halley's Comet is the most famous of these, a Kuiper Belt refugee that swings by Earth every 76 years. Its last visit in 1986 and its next expected in 2061. What makes these comets special is their predictability. Because they're relatively close and influenced by the giant planet's gravity, astronomers can track their orbits with precision, turning them into well-known celestial landmarks. Long-period comets, on the other hand, are the wild cards of the solar system. These enigmatic visitors, like Hale-Bopp or the recently discovered comet Neowise, arrive from the Oort cloud, a realm so distant that their orbits can take thousands or even millions of years to complete. Unlike the orderly, flat plane of the Kuiper Belt, the Oort cloud's icy bodies drift in all directions, meaning long-period comets can approach the Sun at any angle. Their journeys begin when a passing star, galactic tide, or even a collision perturbs their orbit, sending them plummeting toward the inner solar system in a one-time spectacle. Hale-Bopp, for instance, won't return for another 2,400 years, its orbit shaped by gravitational kicks we can only theorize about. The differences between these comets go beyond their orbits. Short-period comets, seasoned by frequent solar encounters, tend to be darker and more depleted, their volatile ices long since boiled away. Long-period comets, fresh from the deep freeze, often glow brighter and display more spectacular tails, their pristine surfaces releasing gases and dust untouched since the solar system's infancy. Some, like Comet Ison, disintegrate entirely during their first and only plunge past the sun, their fragile structures unable to withstand the heat. Studying these icy travelers gives us more than just a light show. It's a way to sample the solar system's raw materials without leaving Earth. Missions like Eris's Rosetta, which landed on Comet 67P, revealed complex organic molecules, hinting that comets may have delivered the building blocks of life to our planet. Meanwhile, the upcoming Comet Interceptor mission aims to catch an Oort cloud comet on its maiden voyage, offering a glimpse of chemistry unchanged for billions of years. From Halley's dependable returns to Hale-Bopp's fleeting brilliance, comets bridge the gap between Earth and the solar system's frozen frontiers. They remind us that the distant Kuiper Belt and Oort cloud aren't just static relics, they're dynamic regions, occasionally sending pieces of themselves hurtling our way, each one a frozen postcard from the edge of everything we know. The Kuiper Belt isn't just a random assortment of icy debris, it's a carefully organized cosmic neighborhood with distinct districts housing different classes of objects. At its core are the classical Kuiper Belt objects, the quiet suburbanites of this frozen realm. These worlds orbit in relatively circular paths, undisturbed by Neptune's gravity, like Pluto and its largest moon, Charon. Their stable orbits suggest they've been here since the solar system's birth, untouched by the planetary migrations that reshaped other regions. Picture them as cosmic archivists, preserving the original layout of the outer solar system like a snapshot frozen in time. Then there are the resonant objects locked in precise gravitational dances with Neptune. For every 2 orbits Neptune completes, these icy bodies circle the sun exactly 3 times, a rhythm so precise it keeps them safe from disruptive encounters. This orbital harmony, known as a 3-to-2 resonance, is why Pluto never collides with its giant neighbor despite their paths crossing. Other resonant objects follow different patterns, like 1-to-2 or even 5-to-4 ratios, creating a celestial symphony of synchronized motion. These gravitational relationships act like cosmic traffic signals, preventing chaotic collisions and maintaining order in the solar system's distant outskirts. The scattered disk objects are the Kuiper Belt's wildcards, icy rebels with stretched, chaotic orbits that take them far beyond the main belt. Unlike their classical cousins, these bodies were violently scattered outward by Neptune's gravity long ago. Their paths stretched into extreme ellipses that can plunge them close to the sun before flinging them back into the deep freeze. Eris, the dwarf planet that helped dethrone Pluto, belongs to this group, tracing an orbit so elongated it spends most of its time nearly 3 times farther out than Pluto. These scattered nomads are crucial to understanding how the giant planets reshaped the early solar system, their erratic paths serving as gravitational fingerprints of ancient planetary migrations. What ties all these objects together is their icy makeup, a blend of frozen gases and organic compounds that reads like a recipe for the early solar system. Water ice dominates, forming the bedrock of most Kuiper Belt worlds, but it's far from alone. Methane ice coats many surfaces, giving objects like Pluto and Eris their distinctive reddish hues as sunlight breaks down this volatile compound over eons. Ammonia hydrates lurk beneath the surface, possibly acting as antifreeze that keeps subsurface oceans liquid on larger bodies. Even rarer ices like nitrogen and carbon monoxide have been spotted, with Pluto's heart-shaped glacier containing enough frozen nitrogen to blanket entire continents. The real surprise is how chemically diverse these distant worlds are. Some Kuiper Belt objects appear dark and carbon-rich, their surfaces cooked by eons of cosmic radiation into complex organic goo. Others gleam brightly, their fresh ice exposed by recent impacts or geological activity. This variation suggests the belt isn't a monolithic zone, but a layered record of the solar system's chemical evolution, with different regions preserving different chapters of the story. The classical objects might represent the original building blocks, while scattered disk members could show how those materials transformed under extreme conditions. Add to this mix the Kuiper Belt's many binary systems, pairs of objects orbiting each other in delicate gravitational balance, and the picture grows even richer. These cosmic duos, making up an estimated 10 to 15% of Kuiper Belt objects, offer clues about how small bodies stuck together in the early solar system. Their prevalence suggests gentle collisions were common, with ice chunks merging like snowballs rather than shattering in violent crashes. Some binaries even have moons of their own, creating miniature solar systems in microcosm. The more we study these distant ice worlds, the clearer it becomes the Kuiper Belt structure isn't random chaos but a fossilized record of gravitational sculpting. Its zones and populations map the solar system's turbulent youth, with each class of objects telling part of a larger story about how planets form, migrate, and shape their surroundings. From the orderly classical belt to the scattered disk's gravitational graffiti, this frozen frontier preserves a cosmic history book written in ice and rock, waiting for us to decode its chillingly beautiful secrets. The Oort cloud's boundaries are so vast and faint that they blur the line between our solar system and interstellar space. Unlike the Kuiper Belt, where telescopes can spot reflected sunlight bouncing off icy surfaces, the Oort cloud's objects are simply too distant and dark to see directly. At these extremes, the sun's light is weaker than a candle flame viewed from miles away, leaving most of this frozen realm hidden in perpetual twilight. Yet despite its invisibility, the Oort cloud's presence is undeniable, written in the paths of comets that streak unexpectedly into the inner solar system, their orbits tracing back to this distant shell like cosmic breadcrumbs. These icy visitors are our primary clues to the Oort cloud structure. Long-period comets like Comet Hale-Bopp arrive on orbits so elongated they must originate from a region thousands of times farther than Earth's distance from the Sun. Their trajectories aren't random, they cluster in ways that suggest a spherical reservoir of icy bodies, some nudged inward by passing stars or the Milky Way's gravitational tides. When astronomers track these comets backward, their paths converge on the Oort cloud's theoretical borders, a celestial crime scene where indirect evidence paints a picture of an invisible culprit. Even more telling are the comets that approach the Sun at extreme angles, some soaring almost perpendicular to the solar system's flat plane. This chaotic distribution couldn't come from the orderly Kuiper Belt. It points to a three-dimensional halo of objects, their orbits scrambled over eons by gravitational encounters. Occasionally, a comet like Comet Ison appears with an orbit suggesting it's visiting the inner solar system for the first, and possibly last time, a pristine refugee from the Oort cloud's deepest reaches. These dynamically new comets are time capsules, their yaws unaltered by previous solar encounters, offering glimpses of chemistry frozen since the solar system's birth. But comets aren't the only evidence. Subtle gravitational anomalies in the outer solar system hint at unseen masses, possibly Oort cloud objects too faint to spot but massive enough to exert a tiny pull on spacecraft like Voyager. Some astronomers even speculate that hypothesized planets like Planet 9 could be disturbing the cloud's inner fringe, sending icy bodies cascading inward. Meanwhile, studies of other star systems reveal similar debris clouds around young suns, suggesting our Oort cloud isn't unique but part of a universal planetary architecture. The cloud's invisibility makes it a frontier of deduction as much as discovery. Mathematical models reconstruct its likely population, trillions of icy bodies, some as large as mountains, drifting so sparsely that a spacecraft could pass through without spotting a single one. Yet occasionally, the universe offers a peek. In 2017, the interstellar object Oumuamua zipped through the solar system, its trajectory suggesting it might have originated from another star's Oort cloud. If true, such visitors could mean these distant halos exchange material across light years, turning the Oort cloud into a cosmic crossroads where our solar system meets the galaxy. Every new long-period comet is a messenger from this unseen realm, its arrival rewriting our understanding of the solar system's farthest reach. Until technology catches up, perhaps with next-generation telescopes capable of spotting these dim, distant objects, the Oort cloud will remain a ghostly outline traced in comet trails and gravitational whispers, a reminder that some of the universe's greatest mysteries hide in plain sight just beyond the edge of vision. After its historic Pluto flyby in 2015, NASA's New Horizons spacecraft wasn't done making history. With Pluto shrinking in its rearview mirror, the intrepid probe set its sights on an even more primordial target, a tiny, bilobed Kuiper Belt object nicknamed Arrokoth, a name meaning sky in the Powhatan language. This snowman-shaped relic, discovered years after New Horizons launched, became the most distant object ever visited by a human-made spacecraft when the probe raced past it on New Year's Day 2019. What it revealed wasn't just another icy rock, but a time capsule from the solar system's infancy, preserved in stunning detail. Arrokoth's two lobes, gently fused together like cosmic putty, told a story of planetary birth far gentler than the violent collisions once imagined. Its smooth surface, unmarked by craters, suggested it formed from a slow-motion merger of two smaller bodies, a process more like a careful handshake than a head-on crash. This contact binary structure offered the first direct evidence supporting the theory that planetesimals, the building blocks of planets, grew through gradual accumulation in the outer solar system's frozen stillness. No longer just a theory, Arrokoth became physical proof of how tiny ice grains could evolve into worlds. The science didn't stop there. Spectroscopic data revealed Arrokoth's surface was coated in methanol ice and complex organic molecules, its reddish hue hinting at tholins, the same carbon-rich compounds found on Pluto and Titan. These findings suggested that the chemistry for life's ingredients wasn't confined to the inner solar system, but might have been widespread in its coldest reaches. Even more striking was the absence of fractures or stress marks where its two lobes met, implying the merger happened at speeds slower than a walking pace, a cosmic dance frozen in time for billions of years. New Horizons cameras captured Arrokoth in unprecedented detail, showing a surface so pristine it appeared almost sculpted. Unlike the battered moons of the inner solar system, this tiny world had avoided the chaos of planetary formation, its contours shaped solely by the gentle forces of its distant environment. The mission team compared it to finding a fossil perfectly preserved in ice, one that hadn't just survived but had never been disturbed. But the journey didn't end with Arrokoth. New Horizons continued piercing deeper into the Kuiper Belt, its instruments scanning for other distant objects while measuring the region's dust and plasma environment. Each transmission back to Earth added another piece to the puzzle, from the surprising lack of small Kuiper Belt objects suggesting fewer collisions than expected to the detection of unexpected ultraviolet glow that might trace to a hidden hydrogen wall at the solar system's edge. Even now, as New Horizons speeds toward interstellar space, it remains a vital scientific tool. With power enough to operate into the 2030s, the spacecraft could potentially target another Kuiper Belt object if one lies within reach. Meanwhile, its data keeps reshaping textbooks, proving that Pluto and Arrokoth aren't oddities but ambassadors of a vast, dynamic frontier we're only beginning to understand. Every pixel beamed back from the Kuiper Belt's frozen depths rewrites what we know about our cosmic origins, and New Horizons isn't done teaching us yet. Arrokoth's peculiar shape, two distinct lobes fused together like a celestial snowman, isn't just a curiosity. It's a frozen snapshot of how the building blocks of planets came to be. When New Horizons captured its first high-resolution images, scientists expected to see a battered, cratered surface typical of ancient objects. Instead, they found a world so smooth it looked polished, with no signs of violent collisions or fractures. This pristine condition suggests Arrokoth formed through an extraordinarily gentle process known as hierarchical accretion, where tiny particles slowly stuck together over millions of years, growing larger without ever experiencing the high-speed crashes once thought necessary for planet formation. The binary lobe structure tells an even more fascinating story. The two halves, unofficially nicknamed Wenu and Weo, have nearly identical composition but slightly different colors, hinting they might have formed separately before merging in a slow-motion embrace. Their smooth connection point lacks the cracks or compression marks you'd expect from a violent impact. Instead, it resembles two snowballs pressed together in microgravity, a testament to the incredibly low speeds at which these primordial bodies combined. Some estimates suggest they collided no faster than human walking pace, their mutual gravity doing the work over eons rather than brute force. Surface details add another layer of intrigue. Arrokoth's reddish hue comes from complex organic molecules called tholins, created when methane ice is bombarded by cosmic radiation over billions of years. But unlike Pluto, where geological activity has refreshed its surface, Arrokoth's tholins are uniformly distributed, proof it's been untouched by heat or resurfacing events since its formation. Spectral analysis also detected methanol ice and water ice mixed with darker organic material, a cocktail of compounds that might have been common in the early solar system's icy outskirts. These ingredients, preserved in deep freeze, mirror the organic-rich environments thought to seed the chemistry for life elsewhere. Perhaps most startling was the absence of small craters. Models predicted Arrokoth should be pockmarked from collisions with smaller Kuiper Belt objects, yet its surface showed only a handful of dimples. This suggests the outer solar system was far less chaotic during planet formation than previously believed, with fewer rogue objects flying around to cause impact. Alternatively, Arrokoth's porous, fluffy texture, like a snow compacted under minimal gravity, might have allowed small impactors to sink in without leaving permanent scars, a feature never before seen on such a primitive body. Every detail aligns with a radical revision of how planetary building blocks assembled. Instead of chaotic, high-speed collisions, the early Kuiper Belt seems to have been a place of patience, where icy particles gently clumped together in the quiet dark. Arrokoth's two lobes likely began as independent planetesimals orbiting each other before their mutual gravity drew them into a final, careful merger. This slow dance, preserved in ice for over 4 billion years, challenges older theories that portrayed planet formation as a violent demolition derby. Now, scientists envision a process more like a carefully choreographed ballet, where delicate gravitational interactions matter more than brute force. The implications stretch far beyond our solar system. If objects like Arrokoth formed this way, similar processes might shape planetary systems around other stars. Its existence suggests that gentle accretion could be a universal mechanism, operating wherever cold, distant debris disks give birth to new worlds. For astronomers, this tiny world has become a Rosetta Stone for decoding planetary origins, a reminder that sometimes the most profound cosmic secrets hide in the quietest corners of the universe. New Horizons data continues to reveal surprises years after the flyby, with researchers still combing through the treasure trove of information it sent home. Each new analysis peels back another layer of mystery, proving that even the smallest, most distant worlds can rewrite our understanding of the solar system's story. Arrokoth isn't just a relic, it's a portal to the past, offering a glimpse of the gentle processes that built the foundations of everything we know. At the farthest edges of the Oort cloud, where the sun's light fades to a dim glow and the pull of distant stars begins to rival our own, there could be worlds lurking in the darkness, hidden giants we've yet to discover. The sheer scale of this region defies comprehension, spanning such vast distances that even a planet the size of Earth could evade detection indefinitely. But mathematics doesn't lie. Strange gravitational tugs on objects at the solar system's fringe have led astronomers to ask, could something massive be waiting in the shadows? The most tantalizing clue comes from a group of extreme trans-Neptunian objects, icy bodies with orbits so stretched and tilted they shouldn't exist. These anomalies all cluster in a way that suggests an unseen gravitational hand guiding them. Enter Planet 9, a hypothetical world up to 10 times more massive than Earth, orbiting hundreds of times farther than Pluto. Its existence was first proposed in 2016 to explain these orbital oddities, and while no telescope has yet spotted it, the mathematical case remains compelling. If real, this wouldn't be a traditional planet but a rogue, something ejected during the solar system's violent youth and now drifting in the Oort cloud's inner reaches. But Planet 9 isn't the only possibility. The Oort cloud could host an entire population of stealth worlds, dwarf planets too distant and dark to reflect sunlight but massive enough to perturb comets. Some might be ice-rich super-Earths, remnants of failed planetary cores that never grew to full size. Others could resemble Sedna, a known dwarf planet with a bizarre 11,000-year orbit hinting at past encounters with unseen neighbors. The challenge is distance. Spotting these objects requires detecting their faint thermal glow against the icy void, a task like searching for a single candle flame in a blizzard. Ongoing surveys are narrowing the hunt. Telescopes like the Vera Rubin Observatory, set to begin scanning the skies in 2025, could finally catch these ghosts in their lenses. Meanwhile, astronomers are re-examining old data for overlooked clues, slight infrared blips or unexpected comet trajectories that might point to hidden masses. Some even speculate that interstellar interlopers like Oumuamua could be fragments from collisions between undiscovered Oort cloud dwarfs, ejected into the galaxy like cosmic shrapnel. The implications go beyond curiosity. Finding such worlds would rewrite the solar system's history, suggesting our planetary family was once far larger and more chaotic. Their compositions might reveal whether our sun stole material from passing stars or if these objects contain pristine ices from the Milky Way's birth cloud. Every hypothetical discovery peels back another layer of the Oort cloud's mystery, not just as a frozen graveyard, but as a dynamic frontier where the line between our solar system and the galaxy blurs. Until we see them, these worlds remain celestial phantoms, whispering their presence through mathematics and orbital disturbances, beckoning us to look deeper into the dark. Neptune isn't just another ice giant, it's the cosmic architect of the Kuiper Belt. Its gravity carving out precise patterns in this distant realm like an invisible chisel shaping ice. The most striking example is Pluto, whose peculiar orbit locks it into a delicate dance with Neptune, completing exactly 2 laps around the Sun for every 3 of Neptune's. This rhythm, known as a 3-to-2 resonance, isn't just a celestial coincidence. It's a gravitational lifeline, ensuring Pluto and Neptune never collide despite their paths crossing. Imagine 2 runners on a circular track, one lapping the other at precise intervals. Their timing creates a stable loop where they never bump, just as Neptune's gravity nudges Pluto into a safe, repeating pattern. But Pluto isn't alone. The Kuiper Belt teams with objects caught in similar resonant harmonies, each group tracing orbits synced to Neptune's movements like gears in a cosmic clock. Some follow a 2-to-1 resonance, circling twice for every Neptune orbit, while others adhere to rarer ratios like 5-to-4 or even 7-to-4. These resonances aren't random, they're evidence of Neptune's ancient migration. Billions of years ago, as the ice giant drifted outward from the Sun, its gravity herded smaller icy bodies into these stable zones, clearing some regions while crowding others. The result, a Kuiper belt partitioned into distinct neighborhoods, each with its own orbital signature. The process works like a gravitational filter. As Neptune moved, its pull acted like a sieve, scattering some objects into chaotic orbits while trapping others in resonant safe havens. the survivors, Pluto among them, avoided ejection or collision by locking into these predictable rhythms. This explains why certain zones of the Kuiper Belt appear densely populated while neighboring stretches seem eerily empty. Neptune's influence didn't just shape where objects ended up, it determined their fates, favoring those that found harmony with its motion and banishing the rest to the solar system's outskirts. These resonant orbits also act as cosmic time capsules. Their stability means the objects within them have survived virtually unchanged since the solar system's infancy, preserving clues about Neptune's journey and the primordial conditions of the outer solar system. When New Horizons visited Pluto, it didn't just study a dwarf planet, it probed a preserved relic of this migration epoch, its geology and composition offering hints about the forces that sculpted its orbit. Even Pluto's atmosphere, which fluctuates dramatically as it swings closer to the Sun, carries echoes of these ancient gravitational battles. Yet Neptune's sculpting isn't just history, it's an ongoing process. The ice giant's gravity still tweaks Kuiper Belt orbits today, subtly adjusting their paths over millennia. Occasionally, an object escapes its resonance, flung inward to become a comet or outward toward the Oort cloud. Others, like Pluto, remain locked in their dances, their rhythms so precise that astronomers can predict their position centuries in advance. This dynamic interplay reminds us that the Kuiper Belt isn't a static museum exhibit but a living laboratory, where gravity's invisible hand continues to shape the solar system's farthest reaches. The deeper we look, the clearer it becomes. Neptune's gravitational fingerprint is everywhere in the Kuiper Belt, from the orderly resonant populations to the scattered debris of its chaotic past. These patterns aren't just celestial curiosities, they're the encrypted language of planetary migration, waiting to be decoded by every mission that ventures into the frozen dark. The Oort cloud isn't just floating in isolation, it's constantly nudged and reshaped by the Milky Way itself, a cosmic dance where the gravity of passing stars and the galaxy's tidal forces act like invisible hands plucking comets from the darkness. Picture the Oort cloud as a vast, loosely bound snow globe, where even the gentlest outside influence can send icy fragments spiraling inward toward the Sun. Over millions of years, stars drifting nearby like Skol's star, which grazed our solar system just 70,000 years ago, have come close enough to disturb this delicate balance. Their gravitational whispers ripple through the cloud, altering orbits just enough to dislodge frozen wanderers and send them on million-year journeys to the inner solar system. But it's not just stellar interlopers at work. The Milky Way's own gravity exerts a slower, grander influence. As the Sun orbits the galaxy, it bobs slightly above and below the galactic plane, creating tidal forces that stretch and compress the Oort cloud over eons. These galactic tides act like a slow-motion sieve, shaking loose comets that happen to be in just the right position at the wrong time. Some calculations suggest this process could be even more effective than passing stars at sending comets our way, especially for objects in the Oort cloud's outer fringes where the Sun's grip is weakest. The result, a cosmic lottery where gravitational nudges determine which icy bodies become visible comets and which remain forever in the dark. Long-period comets like Comet Hale-Bopp or Comet Hypothetical might owe their dazzling appearances to stellar encounters that occurred before human civilization began, their orbits finally decaying enough to fall sunward after millennia in deep freeze. Other comets could be first-time visitors, flung inward by a recent galactic tide or a star's distant passage like Comet Ison, which disintegrated during its maiden plunge past the Sun in 2013. Its fragile structure unable to withstand the heat after billions of years in deep space. These interactions don't just supply our skies with comets, they also leave forensic clues about the Oort cloud structure. By tracing the paths of incoming comets, astronomers can map where in the cloud they originated, revealing hidden density variations or gravitational hotspots. Some researchers even speculate that certain comet clusters might trace back to specific stellar encounters, like breadcrumbs leading to ancient cosmic trespassers. Others suggest the Oort cloud could contain interstellar interlopers captured during these flybys, icy souvenirs from stars that brushed past our solar system long ago. The deeper mystery is how often these disturbances occur. Current estimates suggest a star passes within 1 light year of the Sun every 50,000 years or so, close enough to stir the Oort cloud's outer layers. But with improved data from missions like Gaia, which maps stellar motions with unprecedented precision, astronomers are discovering more past and future close encounters than previously thought. Some simulations now indicate that over the Sun's 4.5 billion-year lifespan, dozens of stars may have plowed through the Oort cloud's inner regions, each scattering comets like a child kicking through autumn leaves. What makes this process so fascinating is its unpredictability. Unlike the orderly resonant orbits of the Kuiper Belt, the Oort cloud's chaotic ballet with the galaxy means comets can arrive from any direction at any time, no two alike in composition or trajectory. Some might be pristine relics carrying unchanged chemistry from the solar system's birth, while others could be fractured remnants of larger bodies shattered by eons of gravitational stress. Each new visitor is a surprise package, its contents hinting at secrets buried in the cloud's frozen depths. The next time you spot a comet streaking across the night sky, remember, its journey likely began with a gravitational nudge from a star you'll never see or a tide you'll never feel. A reminder that even the most isolated corners of our solar system are part of a much larger, dynamic galactic neighborhood. The Kuiper Belt and Oort cloud are the solar system's ultimate deep freezers, places so cold that atoms nearly stop moving, where temperatures hover just a few degrees above absolute zero, the coldest possible temperature in the universe. In these frozen wastelands, the Sun is reduced to a barely noticeable speck, its warmth so faint that a snowflake on Earth receives more heat than entire mountains of ice out here. This isn't just cold, it's the kind of cold that transforms gases into solid landscapes, where methane freezes into pinkish glaciers and nitrogen piles up like powdery snow. Time moves differently in these depths. A single orbit around the Sun can take millennia, even millions of years, meaning an object drifting here might experience fewer seasonal changes than Earth has had civilizations. Such extreme preservation has turned these regions into cosmic time capsules. The ice-coating Kuiper Belt Objects isn't just frozen water. It's a layered archive, trapping dust grains and organic molecules exactly as they were over 4 billion years ago. On Earth, erosion and tectonic activity constantly reshape the surface, wiping away ancient history. But in the Kuiper Belt and Oort cloud, the same patch of ice might remain untouched since the solar system's birth, its chemistry unchanged by heat or liquid water. When NASA New Horizons spacecraft examined Pluto's surface, it found methane ice that had been reddened by cosmic rays over eons, a slow-motion weathering process that would be erased in days on a warmer world. The darkness is just as profound. In the inner Oort cloud, sunlight is already 1/10,000th as bright as on Earth, not enough to cast shadows or warm a surface. Venture farther out, and the Sun blends into the starfield, its light taking weeks to reach these distances. This perpetual twilight means chemical reactions that would happen instantly near Earth could take centuries here. A molecule broken apart by radiation might wait millennia before finding another particle to react with, creating bizarre hybrid compounds unseen anywhere else. Some scientists speculate that certain ices in these regions could exist in exotic crystalline forms impossible under warmer conditions, structures that might revolutionize our understanding of material science if we could study them up close. Yet these extreme conditions have preserved something priceless, raw ingredients from the solar system's birth. Comets like Hale-Bopp, which likely originated in the Oort cloud, contain amino acids and complex organic molecules, the same building blocks that may have seeded life on Earth. In the Kuiper Belt, objects like Arrokoth show no signs of the collisions that battered the inner planets, their surfaces pristine records of gentle accretion. Even their colors tell a story, the reddish hues of Tholin's organic goo cooked up by eons of cosmic radiation, contrast with bright patches of fresh ice exposed by rare impacts. Each hue and texture is a page from a cosmic recipe book, showing how simple ices evolve under the universe's most unforgiving conditions. What makes these regions truly unique isn't just their cold or darkness, but how these extremes interact. The lack of heat means chemical processes that would take seconds on Earth unfold over geological timescales here, creating bizarre hybrids like methane water clathrates ice cages trapping gas molecules in crystalline prisons. The perpetual night allows ultra-frozen volatiles like carbon monoxide to linger on surfaces where sunlight would vaporize them instantly elsewhere. These aren't just dead relics, but slow-motion laboratories where the universe conducts experiments in chemistry and physics we can't replicate anywhere else. Voyager probes have measured temperatures as low as -390 degrees Fahrenheit near the Kuiper Belt's edge, so cold that even atoms vibrate at a fraction of their normal energy. For all their hostility, these frozen frontiers may hold answers to our warm, watery world's origins. The same ices that coat distant objects like Sedna or Quaoar could mirror the compounds that bombarded early Earth, delivering the water in our oceans and the carbon in our bodies. Some models suggest the Oort cloud might even preserve interstellar material predating our Sun, an icy museum of the galaxy's history waiting beyond the light. As telescopes and probes push farther into these twilight zones, each discovery peels back another layer of the solar system's hidden memoirs, written in frost and darkness. The next frontier of solar system exploration lies in ambitious missions designed to pierce deeper into the Kuiper Belt and Oort cloud than ever before. NASA's proposed interstellar probe aims to do just that, a spacecraft built to journey 1,000 astronomical units from the Sun, far beyond Pluto's orbit, into the uncharted territory where the Kuiper Belt gives way to the Oort cloud's frozen halo. Unlike Voyager's serendipitous path, this mission would intentionally target scientifically valuable objects, equipped with modern instruments capable of analyzing surface composition, magnetic fields, and even the elusive boundary where the Sun's influence wanes against the interstellar medium. Imagine a spacecraft designed not just to drift through these regions, but to actively study them, mapping the distribution of icy bodies and testing theories about the solar system's formation with every passing mile. Equally exciting is ESA's Comet Interceptor, a mission poised to ambush a pristine long-period comet, likely a first-time visitor from the Oort cloud, as it streaks toward the inner solar system. Stationed at Lagrange Point 2, a gravitational parking spot a million miles from Earth, the spacecraft will lie in wait until astronomers spot a suitable target. Once unleashed, it could intercept a comet like Hale-Bopp or Hypothetical, capturing high-resolution images and even landing a probe to drill into primordial ice untouched by solar heating. The goal: to sample material that's been frozen since the Sun's birth, potentially containing organic molecules that predate Earth itself. This wouldn't just be a flyby, it'd be a hands-on examination of a cosmic time capsule, revealing whether comets truly delivered life's building blocks to our planet. Private initiatives are joining the hunt too. Projects like Breakthrough Starshot's nanocraft, though aimed at interstellar travel, could pioneer technologies usable in the Kuiper Belt. Think lightweight sails propelled by lasers, capable of reaching Arrokoth's distance in years rather than decades. Meanwhile, advances in telescope technology, from the upcoming Vera Rubin Observatory to next-generation space telescopes, will likely discover thousands more Kuiper Belt objects ripe for exploration, turning what was once a dim frontier into a bustling zone of scientific interest. The challenges are immense. At these distances, solar power is useless, requiring robust nuclear batteries like those on New Horizons. Communication delays stretch to hours, forcing probes to operate with unprecedented autonomy. And with mission timelines spanning decades, the scientists who design these spacecraft may never live to see their full results, a testament to human curiosity's long-term vision. But the potential rewards are cosmic. Every gram of cometary dust, every snapshot of an untouched Kuiper Belt object could rewrite textbooks about our origins. What makes these missions extraordinary isn't just their destinations, but their willingness to embrace the unknown. The Oort cloud's trillion icy bodies and the Kuiper Belt's dynamic geology represent the last unexplored territories of our solar system. As these spacecraft push farther than any human-made object before them, they carry more than instruments. They carry our collective yearning to understand the frozen frontiers where our cosmic story began. Sending a spacecraft to the Kuiper Belt or Oort cloud isn't just a long journey, it's a high-stakes battle against physics itself. The first obstacle hits before a probe even leaves Earth: distance. Pluto, the Kuiper Belt's poster child, is so far that sunlight takes over 4 hours to reach it. Venture to the Oort cloud's inner edge, and that stretch becomes weeks. At these ranges, mission planners can't just hit go and expect real-time control. Every command, a course correction, instrument activation, or even a basic status check faces a round-trip communication delay longer than a workday. New Horizons' flyby of Pluto was a masterclass in patience, with pre-programmed sequences executing flawlessly while Earth-based teams waited hours just to confirm success. Imagine piloting a robot through a maze blindfolded, where every instruction arrives 9 hours late. That's the reality of deep space operations. Power is another relentless foe. Sunlight at Pluto's distance is 1,000 times weaker than at Earth, rendering solar panels nearly useless. That's why missions like New Horizons rely on plutonium-powered batteries, converting radioactive decay into electricity. But these systems degrade over decades, and with the Oort cloud potentially a century's travel away, engineers face a brutal equation: how to keep instruments running when even nuclear fuel's energy output dwindles to a trickle. Some concepts propose revolutionary power sources like compact fission reactors or laser-beamed energy from orbital relays, but these remain untested at interstellar scales. Until then, every watt must be rationed like water in a desert, forcing heartbreaking compromises between data collection and survival. Then there's the cold, not just the biting chill of space, but temperatures so low they threaten to freeze moving parts solid. Lubricants that work flawlessly near Earth turn to glue, metal joints stiffen, and onboard fuel risks becoming slush. Voyager 2's thrusters, still firing after 45 years in the void, require heaters just to stay functional. Future probes might need self-warming systems or exotic materials like metallic glass to avoid seizing up. Even more insidious is cosmic radiation, which fries electronics over time. Without Earth's magnetic field as a shield, microchips endure a constant barrage of high-energy particles, necessitating hardened circuitry or redundant backups that add weight and complexity. Speed becomes a paradox. To reach these distant realms in a human lifetime, spacecraft must travel faster than any probe before, yet high velocity creates new problems. At 15 kilometers per second, a dust particle no larger than a grain of sand carries the kinetic energy of a bowling ball, meaning shielding must balance weight and protection. Faster trajectories also leave less time for science during brief flybys, forcing engineers to choose between thorough data collection and ever-elusive distance records. Some propose orbiter missions, but slowing down at these distances would require impractical amounts of fuel, leaving most probes as fleeting tourists rather than long-term observers. Perhaps the greatest challenge is time itself. A mission to the Oort cloud could span generations, with scientists who design it unlikely to witness its climax. New Horizons took 9 years just to reach Pluto. A trip to the Oort cloud might require 50. This tests not just technology but human perseverance, demanding funding and focus across political eras and cultural shifts. Solutions range from AI autonomy to citizen science involvement, ensuring public engagement doesn't fade before the payoff arrives. Yet these hurdles haven't stopped innovation. NASA's Dragonfly mission to Titan is pioneering nuclear-powered drones, while breakthrough Starshot experiments with laser-propelled nanocraft. Each breakthrough, whether in propulsion, power, or communication, chips away at the barriers guarding the solar system's frozen frontier. What seems impossible today might be routine tomorrow, because if history shows us anything, it's that humanity's hunger to explore always finds a way. The Oort cloud may be the solar system's outermost frontier, but its boundaries aren't closed occasionally. The universe sends visitors crashing through its icy expanse. In 2017, astronomers spotted Oumuamua, a bizarre, cigar-shaped object hurtling through our cosmic neighborhood at breakneck speed. Its trajectory left no doubt this wasn't just another comet from our own Oort cloud. It was an interstellar interloper, the first confirmed visitor from another star system. Then, just 2 years later, another traveler appeared, Comet Borisov, a frozen wanderer trailing a glittering tail of dust and gas. These two cosmic nomads offered something unprecedented, proof that the Oort cloud isn't just a repository of our solar system's history, but a crossroads where alien worlds pass by in the night. What makes these encounters so revolutionary is how they rewrite our understanding of the Oort cloud's role. For decades, scientists assumed this distant shell was a closed ecosystem, its icy bodies orbiting in near-total isolation. But Oumuamua and Borisov shattered that assumption, revealing that the cloud isn't a static border, it's a dynamic filter, catching and sometimes redirecting material from other star systems. Some researchers now believe the Oort cloud could harbor countless interstellar hitchhikers, icy fragments captured by the sun's gravity as it plowed through dense molecular clouds or drifted near sibling stars in its galactic youth. These trapped interlopers might blend seamlessly with native objects, their origins revealed only by extreme orbits or exotic compositions. The mechanics of this cosmic exchange are as fascinating as they are complex. When a star passes within a few light years of our Sun, something that happens roughly every 50,000 years, its gravity can stir the Oort cloud's outer layers, dislodging some objects while capturing others. Oumuamua likely slipped through this very process, ejected from another star system only to be flung our way by a chance encounter. Borisov, with its more comet-like appearance, hints at a different story. Perhaps it originated in a system rich with volatile ices, only to be torn loose by a gravitational tug-of-war between planets. Either way, their presence suggests the Oort cloud isn't just a relic of our past, it's a living record of the solar system's interactions with the galaxy. The implications reach even further. If interstellar objects are common visitors, they could have played a role in seeding Earth with water or organic molecules long ago. Some theories suggest that during the Sun's early travels through crowded star-forming regions, the Oort cloud might have absorbed foreign ice rich in prebiotic compounds, later delivering them to Earth via cometary impact. Even more tantalizing is the possibility that some of these captured interlopers could be fragments of shattered exoplanets, offering us free samples of alien geology without ever leaving home. Yet detecting these strangers is like finding needles in a galactic haystack. Most would be too dim to spot unless they ventured close to the Sun, and their unusual orbits could easily be mistaken for native Oort cloud objects. The key might lie in their speed or trajectory. Interstellar visitors often move faster or approach from unexpected angles compared to local comets. Upcoming telescopes like the Vera Rubin Observatory, with their ability to scan the entire sky weekly, could spot dozens more of these travelers, helping us gauge just how crowded the Oort cloud's highways really are. One thing is certain, Oumuamua and Borisov were just the beginning. Every new interstellar visitor peels back another layer of the Oort cloud's mystery, revealing a realm where the borders between star systems blur and the universe's debris mingles freely. As we push deeper into this frozen frontier, we're not just exploring the edges of our own solar system, we're opening a window to the galaxy beyond. The Kuiper Belt isn't just a curiosity in our own solar system, it's a Rosetta Stone for decoding how planets form around other stars. Astronomers have spotted hundreds of debris disks orbiting young suns, glowing halos of dust and ice that look eerily familiar. These distant rings, like the famous disk around the star Fomalhaut, bear striking resemblances to our Kuiper Belt but on a grander scale. Some stretch dozens of times wider, their icy particles swirling in vast, luminous bands that hint at unseen planets shaping them from within. By studying our own Kuiper Belt's intricate structure, its resonant orbits, binary objects, and scattered populations, we're essentially peering into a cosmic mirror, glimpsing what exoplanetary systems might have looked like in their infancy. Take the case of HR 8799. A star with 4 giant planets orbiting far beyond where Jupiter sits in our system. Their arrangement suggests they've migrated outward, much like Neptune is thought to have done, potentially sculpting a Kuiper Belt-like region in their wake. The gaps and clumps in these alien debris disks often betray the presence of hidden worlds, their gravity clearing paths or piling up material like snowplows. Our Kuiper Belt's own kernel, a dense concentration of objects just beyond Neptune, might be the faint echo of such planetary nudges, a fossilized clue about how giant planets dance as they mature. What makes these comparisons so powerful is their predictive value. When scientists found strange asymmetries in the debris disk around Beta Pictoris, theories honed in our own Kuiper Belt helped explain them. Just as Neptune's gravity hurls objects into resonant orbits, Beta Pictoris' massive planet, 12 times Jupiter's mass, likely shapes its disk through similar gravitational interactions. Even the warped edges of some disks, like those around O Microscopii, find parallels in our Kuiper Belt's inclined population, objects with steep orbital tilts possibly caused by ancient planetary encounters. These aren't just vague similarities, they're recurring patterns in the universal language of planet formation. The chemistry of these distant disks adds another layer of intrigue. ALMA telescope observations reveal many contain frozen carbon monoxide, a compound also abundant in Kuiper Belt objects like Pluto. Some, like the disk around the young star TW Hydrae, even show signs of water ice in specific ring-like structures, mirroring the ice-rich zones of our own outer solar system. These shared ingredients suggest the processes that built our Kuiper Belt. Gentle collisions, ice migration, and gas giant influences aren't unique to us but part of a galactic playbook for constructing planetary systems. When New Horizons discovered complex organic molecules on Arrokoth, it didn't just rewrite our local history, it hinted that the building blocks for life might be common outcomes in icy debris disks galaxy-wide. Perhaps most tantalizing is how these comparisons refine our search for Earth-like worlds. Debris disks often show bright inner rings and darker outer regions, hinting at frost lines, boundaries where different ices condense. Our Kuiper Belt marks where water gives way to methane and nitrogen ice, a transition zone that may have shaped where planets could form. Studying how these frost lines vary around other stars helps identify where rocky, potentially habitable planets might emerge in their systems. Some researchers even speculate that the Kuiper Belt's relative poverty, its lack of massive objects compared to some exo-disks, could be why our inner solar system remained calm enough for life to arise. Systems with more crowded belts might bombard their inner planets with comets, creating hostile environments. Every mission to the Kuiper Belt, every pixel beamed back from New Horizons, doubles as a key to unlocking exoplanet mysteries. When we map Arrokoth's gentle merger or trace Pluto's nitrogen glaciers, we're not just exploring our backyard, we're developing a universal grammar for understanding how chaos and gravity sculpt worlds everywhere. The next generation of telescopes, from the James Webb Space Telescope to the Extremely Large Telescope, will test these connections further, peering into young systems where Kuiper belts are still taking shape. What we learn from our own frozen frontier may one day help us read the stories of planets we'll never see up close, written in the icy annals of their distant debris disks. The Oort cloud doesn't just mark the edge of our solar system, it exists in a cosmic twilight zone where the sun's grip weakens and the galaxy's influence takes over. Picture the heliopause, that invisible boundary where the solar wind collides with interstellar space, creating a turbulent buffer between our star's domain and the vast expanse beyond. The Oort cloud's inner fringes brush against this chaotic frontier, its icy inhabitants orbiting in a region where the sun's gravity is barely stronger than the Milky Way's collective pull. At these extremes, the rules change. A passing star's nudge or the gentle tug of a galactic tide can redirect a comet's path as easily as the sun's diminishing gravity, turning the outer Oort cloud into a dynamic crossroads between solar and interstellar space. This overlap creates a celestial balancing act. While the inner Oort cloud remains firmly bound to the sun, its outer layers are so tenuously connected that astronomers debate where solar influence truly ends. Some models suggest the cloud's outermost objects might orbit at distances where the Milky Way's tidal forces rival the sun's, meaning their paths are shaped as much by the galaxy's gravitational field as by our own star. This delicate equilibrium explains why long-period comets, like those from the Oort cloud, arrive from all directions rather than following the flat plane of the solar system. Their orbits aren't just stretched, they're randomized by eons of subtle galactic nudges, like leaves caught in a slow-motion whirlwind. The heliopause itself adds another layer of complexity. As Voyager 1 and 2 crossed this boundary, they revealed a turbulent region where charged particles from the sun clash with interstellar plasma, creating a magnetic froth that might interact with the Oort cloud's outermost ice. Some theories propose that this interaction could occasionally kick loose comets inward, sending them spiraling toward the inner solar system. Others suggest the heliopause's pressure might compress the Oort cloud's outer edge, creating a denser shell of objects just beyond its reach, like snow piling up against an invisible fence. What makes this frontier so fascinating is its impermanence. Over millions of years, as the sun orbits the galaxy, it drifts through regions of varying stellar density. In sparse zones, the Oort cloud might expand outward, its boundaries stretching as the sun's gravity faces less competition. But in dense star-forming regions or during close encounters with other stars, the cloud could contract, its outer layers stripped away or reshuffled. This means the Oort cloud isn't a static structure but a shape-shifting entity, its edges breathing in and out over cosmic timescales. The implications ripple across astronomy. If the Oort cloud's outer reaches are this malleable, they might serve as a cosmic net, catching interstellar objects like Oumuamua as they pass through. Over billions of years, our solar system could have accumulated a significant population of such hitchhikers, their presence hidden among native icy bodies. Future missions equipped to detect chemical or isotopic anomalies might one day distinguish these interstellar refugees from local comets, offering a glimpse into how star systems exchange material across the void. Yet for all its grandeur, this boundary remains frustratingly elusive. No probe has come close to the Oort cloud's inner edge, let alone its outer fringes. Voyager 1, humanity's farthest-flung spacecraft, won't reach the cloud's outskirts for another 300 years. Until then, we're left with mathematical models and the occasional comet as messengers, each one hinting at the invisible forces sculpting the solar system's final frontier. What's clear is that the Oort cloud doesn't just end, it fades, its outermost objects blending into the galactic background like whispers in a storm. This gradual transition reminds us that even the mightiest star's influence has limits, and that our solar system, for all its vastness, is just a speck in the Milky Way's grand tapestry, one whose edges are still being written. When people picture the Kuiper Belt, they often imagine a chaotic asteroid field like those in sci-fi movies, a dense, impassable sea of tumbling ice and rock. The reality couldn't be more different. If you were to fly through this region, you'd mostly see nothing. The average distance between major Kuiper Belt objects is millions of miles, so vast that a spacecraft could traverse the entire zone without spotting a single icy body. This misconception likely stems from artistic renderings that cram objects close together for visual effect, but in truth, the Kuiper Belt's total mass is less than 1/10 of Earth's, spread across an area wider than the inner solar system. Even the densest clusters have more in common with a few scattered marbles in a football stadium than a packed debris field. Another persistent myth centers on Pluto's status as the Kuiper Belt's king. While it's true Pluto is the brightest and was the first discovered, it's not the largest by mass. That title goes to Eris, a fellow dwarf planet nearly 30% more massive despite being slightly smaller in diameter. This counterintuitive fact reveals Eris's rocky core must be denser than Pluto's icy mantle, rewriting our understanding of how these distant worlds formed. The mix-up persists partly because Pluto's atmosphere reflects more sunlight, making it appear more prominent, while Eris's higher density tells a different story beneath the surface. Then there's the idea that the Kuiper Belt is just a colder version of the asteroid belt. While both are remnants of planetary formation, their compositions tell wildly different stories. Asteroids are largely rock and metal, baked dry by eons of sunlight, while Kuiper Belt objects are cosmic snowballs, mixes of water ice, frozen gases, and organic compounds preserved in deep freeze. This distinction matters because it means the Kuiper Belt isn't just planetary leftovers. It's a frozen archive of the solar system's original ices, largely unchanged since their creation over 4 billion years ago. Some even claim the Kuiper Belt is unchanging, a static museum of the past. New horizons proved otherwise. Pluto's shifting glaciers, Haumea's spinning debris ring, and the recent discovery of volcanic activity on other KBOs reveal a dynamic region where geology still unfolds, albeit in slow motion. The belt's apparent quiet is deceiving. Gravitational interactions constantly reshape orbits, while sublimating ices create temporary atmospheres on worlds like Makemake. This isn't a frozen wasteland, but a place where time moves differently, with processes that take millennia instead of years. Perhaps the most stubborn myth is that these objects are irrelevant to Earth. The truth, Kuiper Belt bodies might hold the keys to our planet's habitability. Their chemistry, rich in water and complex organics, matches the ingredients thought to have seeded early Earth via comet impacts. Some theories suggest the late heavy bombardment, which delivered much of Earth's water, sourced its projectiles from the Kuiper Belt's primordial stockpile. Far from being distant curiosities, these icy worlds could be the cosmic couriers that made our blue planet possible. Dispelling these myths isn't just about accuracy. It reshapes how we understand the solar system's architecture. The Kuiper Belt isn't a crowded junkyard or a stagnant backwater, but a sparsely populated, chemically rich frontier where the rules of planetary science are still being written. Every corrected misconception peels back another layer of assumption, revealing a reality far stranger and more fascinating than fiction. The Oort cloud might seem remote, but its icy inhabitants could have played a starring role in Earth's origin story. 4 billion years ago, during a chaotic era called the Late Heavy Bombardment, our planet was pummeled by countless comets and asteroids, many of which may have originated in this distant reservoir. These frozen messengers didn't just bring destruction, they carried the very ingredients that made Earth habitable. scientists analyzing cometary water have found striking similarities to Earth's oceans with matching ratios of deuterium, a heavy hydrogen isotope. This cosmic fingerprint suggests that long-period comets from the Oort cloud might have contributed significantly to our planet's water supply, turning a molten rock into the blue world we know today. But water wasn't the only gift from the depths. Comets like Hale-Bopp and Hyakutake, believed to be Oort cloud natives, contain complex organic molecules, amino acids, sugars, and even the building blocks of DNA. When these icy travelers slammed into early Earth, their cargo could have jump-started probiotic chemistry, providing raw materials for life's earliest stirrings. Experiments like NASA's Stardust mission, which captured particles from Comet Wild 2, confirmed these compounds survived the harshness of space. Imagine a frigid Oort cloud object, rich in formaldehyde and hydrogen cyanide, plunging into a warm volcanic pond, a perfect laboratory for transforming simple molecules into life's precursors. The timing adds another layer of intrigue. As the giant planets migrated in the young solar system, their gravity likely disturbed the Oort cloud, triggering a downpour of comets toward the inner planets. This bombardment coincided with Earth's cooling crust and the emergence of its first oceans, creating a Goldilocks window where water and organics arrived just as conditions ripened for life. Some models suggest these impacts could have delivered up to half of Earth's water, with the rest coming from closer sources like the asteroid belt. The Oort cloud's role might have been selective but decisive, its comets acting not as the sole suppliers but as cosmic spice traders enriching Earth's primordial soup. Not all scientists agree, of course. Critics point out that some Oort cloud comets have water isotopes too dissimilar to Earth's, implying they couldn't be major contributors. Others argue that intense heat from impacts would have destroyed delicate organic molecules before they could benefit emerging life. Yet recent discoveries complicate this view. When the Rosetta mission studied Comet 67P, it found the amino acid glycine, a key protein component alongside phosphorus, another life-essential element. Even more telling, these compounds were embedded in protective dust grains, which could have shielded them during atmospheric entry like tiny heat-resistant capsules. The debate reveals a deeper truth. The Oort cloud isn't a monolith. Its comets vary wildly in composition, reflecting different formation regions and histories. Some might be interstellar immigrants, while others are pristine relics of our solar system's birth. This diversity means that while not every Oort cloud visitor delivered useful materials, a lucky few could have carried exactly the right cocktail of water and organics to matter. Like a cosmic lottery, Earth might have won the jackpot by capturing just enough of these volatile, rich impactors at the perfect moment. What's certain is that the Oort cloud's influence didn't end with the bombardment. Even today, occasional comets from this distant halo replenish Earth's upper atmosphere with trace organics and water vapor, a faint echo of the ancient deluge that shaped our planet. Every time a long-period comet streaks through the inner solar system, it's a reminder that the boundary between Earth and its frozen frontier is more porous than it seems. The same processes that built the Oort cloud may have also built us, linking life's origins to the solar system's farthest reaches in ways we're only beginning to understand. Artistic visions of the Kuiper Belt and Oort cloud stretch the imagination where scientific rigor meets boundless creativity. Concept artists at NASA and ESA craft painstakingly accurate renderings of these frozen frontiers, blending telescope data with atmospheric lighting effects to make distant worlds feel tangible. Take Pluto's iconic Heart Glacier, first revealed by New Horizons in crisp black and white. When transformed into color by NASA visualizers, its pinkish nitrogen plains and jagged water ice mountains suddenly pulsed with personality. These hyperreal depictions serve a dual purpose. They translate raw data into public understanding while anticipating what future explorers might see. The same artists who visualized Arrokoth's snowman shape before New Horizons arrived later refined their models to match its flattened pancake lobes, proving how art evolves alongside discovery. Yet for every scientifically grounded illustration, there's a sci-fi spectacle that bends the rules. Films like Ad Astra portray the Kuiper Belt as a treacherous navigational hazard, with spacecraft dodging ice boulders like a high-stakes obstacle course, an exaggeration of its sparse reality. Video games like Destiny reimagine these zones as lawless outposts where rogue factions lurk among dwarf planets, while the Expanse novels depict the belt's scarcity of resources fueling political unrest. These dramatizations thrive on tension, compressing astronomical distances into cinematic set pieces. Still, they occasionally nod to reality. Ad Astra's Neptune sequence hauntingly captures the ice giant's windswept majesty, its moons backlit by a sun reduced to a piercing star. The Oort cloud's invisibility invites even wilder interpretations. In Arthur C. Clarke's 2061, it's a realm where primordial ice holds dormant alien life, while Liu Cixin's The Three-Body Problem suggests it could hide extraterrestrial surveillance probes. Concept artists lean into its mystery. Digital paintings often show fractured comets adrift in star-studded blackness, their surfaces etched with strange grooves from eons of cosmic radiation. Some depictions borrow from Hubble's deep field images, framing Oort cloud objects against the Milky Way's glow to emphasize their isolation. The most striking visuals merge fact with fantasy. One essay-commissioned piece overlays a hypothetical Oort cloud comet's trajectory over the actual positions of nearby stars, grounding speculation in astrophysical data. Even music channels this duality. Composer Gene Mitchell Jarre's Oxygen 3 album conjures the cloud's desolation through shimmering synth tones, while Holst's Neptune from the Planets evokes its icy grandeur with haunting choral fade-outs. These artistic choices, whether a film's sound design or a game's environmental soundtrack, shape public perception as powerfully as any textbook. When New Horizons mission scientists collaborated with composer William Zeitler to create a Pluto suite based on the dwarf planet's geological features, they bridged science and art, letting audiences hear the landscapes the probe revealed. What unites these portrayals is their power to make the unimaginable visceral. Whether through a researcher's precise digital model or a filmmaker's dramatic license, these creative works do more than entertain. They invite us to emotionally connect with realms too distant for direct experience. Every brushstroke, frame, or musical note becomes a vessel for wonder, transforming abstract astronomical concepts into something that feels alive, perilous, or beautiful. As our probes push farther into these frozen frontiers, artists will keep reimagining them, ensuring the Kuiper Belt and Oort cloud remain not just subjects of study, but canvases for humanity's collective cosmic dreams. The search for Kuiper Belt objects isn't just for professional astronomers with powerful telescopes. Some of the most exciting discoveries have come from backyard stargazers and citizen scientists armed with nothing more than curiosity and a computer. Amateur astronomers have played a pivotal role in mapping this distant frontier, proving that you don't need a PhD or a NASA budget to contribute to cutting-edge science. In 2011, a German amateur named Rainer Stoss spotted a faint dot moving across telescope images, a dot that turned out to be a new Kuiper Belt object later designated as UZ224. His discovery wasn't luck. It was the result of meticulous data analysis, combing through publicly available sky survey images that professionals simply hadn't had time to scrutinize. Projects like Ice Hunters have taken this collaborative spirit even further, inviting the public to sift through data from telescopes like Pan-STARRS and the Hubble Space Telescope. Participants scan images for slow-moving specks of light, potential KBOs, hidden in vast datasets too large for any single research team to process. The approach works because human eyes excel at pattern recognition, often spotting anomalies that algorithms might miss. Ice Hunters volunteers have flagged hundreds of candidate objects, some of which have been confirmed as genuine Kuiper Belt residents. It's cosmic crowdsourcing at its best, turning a global community of enthusiasts into active participants in planetary science. The impact goes beyond raw numbers. In 2016, amateur contributions helped identify an unusual Kuiper Belt object with an orbit so tilted it challenged existing theories about the solar system's formation. Citizen scientists also played a key role in pinpointing targets for NASA's a New Horizons mission after its Pluto flyby, helping identify potential destinations like Arrokoth among thousands of candidate objects. These collaborations blur the line between professional and amateur, proving that groundbreaking science can happen anywhere from university labs to living rooms. What makes these discoveries so remarkable is their accessibility. Many KBO hunting projects require no special equipment, just an internet connection and patience. Online platforms like Zooniverse host regular campaigns where volunteers classify potential Kuiper Belt objects, often with tutorial guides that make the process approachable for beginners. Some participants have even co-authored scientific papers, their names listed alongside career astronomers in peer-reviewed journals. The legacy of amateur KBO hunters is a testament to the democratization of space exploration. Every time a volunteer spots a distant speck of light that turns out to be a new world, they're not just adding to a catalog, they're helping rewrite the story of our solar system's outermost reaches. And with next-generation telescopes like the Vera Rubin Observatory set to flood astronomers with petabytes of new data, the role of citizen scientists is only growing more vital. The next big discovery might not come from a mountaintop observatory, but from someone scrolling through telescope images on their lunch break, uncovering secrets hidden in plain sight at the edge of the solar system. The frozen wastes of the Kuiper Belt might seem inhospitable, but to future pioneers, they could represent something far more valuable than scientific curiosity. They could become the solar system's gas stations and construction yards. Every drifting Kuiper Belt object is a potential treasure chest of water ice, methane, ammonia, and other volatiles, resources that are scarce in the inner solar system but vital for sustaining human expansion into space. Imagine a future where robotic mining platforms latch onto dwarf planets like Pluto or Makemake, extracting water not just for drinking, but as raw material for rocket fuel. When split into hydrogen and oxygen through electrolysis, water becomes the propellant that could power generations of spacecraft, turning these distant ice worlds into cosmic pit stops for missions headed to the outer planets or beyond. But the challenges are staggering. Mining a Kuiper Belt object isn't like drilling into an asteroid. It's operating in a realm where temperatures plunge below -400 degrees Fahrenheit, where sunlight is 1,000 times weaker than on Earth, and where a single round-trip communication with Earth takes hours. Machinery would need to function autonomously for years, designed to withstand conditions that make Antarctica look balmy. Ice on these bodies isn't loose and powdery. It's often harder than granite, laced with abrasive dust and frozen gases that could clog equipment or trigger explosive sublimation if heated carelessly. And then there's the economics. Transporting mined materials back to where they're needed would require breakthroughs in propulsion, likely involving nuclear-powered tugs or continuous thrust systems we've only theorized about. Despite these hurdles, the incentives are compelling. Water from the Kuiper Belt could be exponentially cheaper to use in space than hauling it up from Earth's gravity well, where every kilogram launched costs thousands of dollars. Companies like TransAstra have already floated concepts for asteroid mining, and while Kuiper Belt operations would be orders of magnitude more difficult, the principle remains the same: harnessing resources where they're abundant rather than dragging them across interplanetary distances. The first targets might not be dwarf planets but smaller, rubble pile objects like Arrokoth, where low gravity would make extraction easier. A single mid-sized KBO could contain more water than all of Earth's oceans, locked in ice that's remained pristine for billions of years. The legal framework is murkier than the technical one. Current space treaties forbid national appropriation of celestial bodies, but commercial exploitation operates in a gray zone. Would mining a Kuiper Belt object count as claiming territory, or simply as collecting materials like scooping up ocean water on Earth? Precedents set by asteroid mining ventures could eventually extend to the Kuiper Belt, but with decades likely passing between investment and payoff, only the most visionary or patient corporations would gamble on being first. Speculative as it seems, the groundwork is already being laid. NASA experiments with in-situ resource utilization on the Moon and Mars are proving that extracting and using off-world materials is feasible. The same technologies, autonomous drills, compact processing plants, and closed-loop life support, could one day be adapted for the Kuiper Belt's extreme environment. Perhaps the first miners won't be humans at all, but self-replicating robot swarms programmed to harvest ice and construct fuel depots for passing spacecraft. The dream isn't just about profit, it's about permanence. A sustainable human presence in space requires leveraging the solar system's natural resources, and the Kuiper Belt's frozen reserves might eventually underpin everything from orbital habitats to interstellar probes. What now seems like science fiction could, in a century or two, be the industrial foundation of a spacefaring civilization, with ice-clad worlds becoming the desert oil fields of the cosmic economy. Until then, every mission that studies these distant objects from New Horizons to its successors is inadvertently scouting the frontier of humanity's next giant leap. The Oort cloud's existence spans billions of years, but its destiny hinges on the Sun's violent transformation in the distant future. As our star exhausts its hydrogen fuel and swells into a red giant roughly 5 billion years from now, its ballooning outer layers will unleash chaos on the solar system's frozen frontier. The inner Oort cloud will face a fiery reckoning. Objects within about 20,000 astronomical units will be bombarded by intense heat and radiation, their ices vaporizing in seconds as the dying sun's diameter expands beyond Earth's orbit. Comets that once took millennia to complete a single orbit will suddenly find themselves plunging into a stellar inferno, their frozen nuclei erupting into brilliant but short-lived streaks of light. But distance offers no guarantee of safety. Even the outer Oort cloud won't escape unscathed. While the Sun's expanded atmosphere won't reach these remote objects, its gravitational grip will weaken dramatically as it sheds nearly half its mass. This sudden loss of pull will destabilize countless icy bodies, sending some careening into interstellar space like marbles released from a slingshot. Galactic tides and passing stars, previously minor nuisances, will become dominant forces, shearing off the Oort cloud's outermost layers and scattering them across the Milky Way. Some simulations suggest up to 90% of the cloud's mass could be lost during this phase, with surviving objects flung into wildly elongated orbits or captured by other stars. The Sun's final act as a white dwarf adds another twist. Shrunken to Earth size but fiercely hot, this stellar ember will still emit enough radiation to slowly erode any remaining icy bodies that stray too close. Yet paradoxically, its extreme density means its gravitational reach remains significant, enough to retain a skeletal version of the Oort cloud, albeit one far sparser and more chaotic than before. The objects that endure will orbit a dimmer, cooler star, their once pristine ices baked by billions of years of cosmic radiation into coal-like organic crusts. What's fascinating is how this process mirrors the solar system's birth in reverse. Just as the young sun's gravity sculpted the Oort cloud from scattered planetesimals, its death throes will dismantle it, returning material to the galactic reservoir from which it came. Some of these ejected ice balls might even become rogue comets, drifting between stars for eons before being captured by another system, potentially delivering water and organics to newborn planets elsewhere in the galaxy. Yet the Oort cloud's legacy could outlast the Sun itself. Models suggest a handful of its most distant objects might remain gravitationally bound to the white dwarf indefinitely, their orbits so vast they complete a single revolution every few million years. These lonely survivors would circle a darkening star in a frozen graveyard, their surfaces bearing silent witness to the solar system's former glory long after Earth and the inner planets have been reduced to ashes. Even in death, the Oort cloud story isn't one of total annihilation but of transformation, its remnants becoming celestial nomads in a galaxy that never stops rewriting its own history. Exploring the frozen frontiers of our solar system isn't just a technical challenge, it's an ethical crossroads. Every dollar spent launching a probe to Pluto or planning a mission to the Oort cloud is money not spent on Earth's pressing needs, climate change, poverty, or healthcare. Critics argue that these distant regions offer no tangible benefit to humanity, their scientific value dwarfed by the urgent problems at our doorstep. Why chase icy ghosts at the edge of darkness when millions lack clean water or stable housing? The debate forces us to weigh curiosity against compassion, ambition against responsibility. Yet scientists counter that the pursuit of knowledge has never been a zero-sum game. The same technologies developed to navigate the Kuiper Belt, miniaturized instruments, advanced propulsion, autonomous systems often spin off into life-saving applications. MRI machines trace their roots to space research, and GPS relies on satellites originally designed for celestial navigation. A mission like New Horizons didn't just photograph Pluto, it pushed the boundaries of low-power computing and deep space communication, innovations that ripple through industries far beyond astronomy. The challenge lies in quantifying these indirect benefits, a task as nebulous as the Oort cloud itself. Ethicists raise deeper questions about our role as cosmic stewards. If we eventually tap the Kuiper Belt's resources, who decides how they're allocated? Would mining ice from Makemake or Haumea exploit celestial bodies that belong to no nation? Or would it democratize access to space by reducing reliance on Earth's dwindling reserves? The Outer Space Treaty of 1967 prohibits territorial claims, but it's silent on commercial exploitation, leaving a legal gray zone. Some argue that untouched worlds like Arrokoth are cosmic heritage sites deserving protection from human interference. Others see them as lifeless reservoirs, their value measured in the opportunities they unlock for our species' survival. The environmental angle adds another layer. Spacecraft like New Horizons are scrupulously sterilized to prevent contaminating pristine environments with Earth microbes, a protocol that could lapse if profit-driven ventures race to exploit these regions. Imagine a future where corporate landers drill into Pluto's glaciers, accidentally introducing bacteria that alter its chemistry forever. The ethical parallels to Earth's colonial history are unsettling. Will we repeat past mistakes by treating celestial bodies as territories to be conquered rather than wonders to be understood? Perspective matters too. For indigenous astronomers, these debates echo older conversations about land and sky. The naming of Arrokoth, a Powhatan word meaning sky, reflects growing recognition that space exploration shouldn't just serve Western scientific narratives. Ethical exploration means collaborating with communities whose cosmologies have long connected Earth to the stars, ensuring that the quest to understand the solar system's fringe enriches all humanity, not just a privileged few. There's no easy answer, but perhaps the question itself is the point. Wrestling with these dilemmas forces us to articulate what kind of civilization we aspire to be. One that retreats inward, or one that reaches outward while lifting up those left behind. The Kuiper Belt and Oort cloud are more than icy waypoints. They're mirrors reflecting our values back at us across the void. How we choose to explore them, or whether we do at all will say as much about humanity as any discovery we might make. The Kuiper Belt and Oort cloud are more than distant relics. They're the solar system's final puzzle pieces, holding answers to questions we've only begun to ask. From Pluto's beating heart of nitrogen glaciers to Arrokoth's primordial snowman shape, these frozen realms have rewritten our understanding of how planets form. The Kuiper Belt, with its orderly orbits and dwarf planets, shows us the solar system's construction zone preserved in ice. Meanwhile, the Oort cloud's ghostly halo of comets whispers secrets about our sun's wild youth and its place in the galaxy. Together, they're a cosmic time machine offering snapshots of chemistry and chaos from over 4 billion years ago. Yet for all we've uncovered, these frontiers remain half-explored. New Horizons' journey to Arrokoth proved even the smallest Kuiper Belt objects are geological wonders, while the Oort cloud's trillion icy bodies still hide in darkness, known only by the rare comets they send our way. Every discovery peels back another layer, like Haumea's surreal rings or Sedna's lonely, elongated orbit, hinting at gravitational dramas we've yet to fully decode. And with missions like Comet Interceptor poised to ambush an Oort cloud visitor, we're on the verge of revelations that could rewrite textbooks. What keeps these regions endlessly fascinating isn't just their past but their future. The Kuiper Belt could one day fuel humanity's expansion into the outer solar system, its ices transformed into rocket propellant for generations of explorers. The Oort cloud, ever shifting under galactic tides, might still hold interstellar travelers like Oumuamua, waiting to reveal how star systems trade material across the void. Even now, as telescopes grow sharper and probes push farther, we're barely scratching the surface of what's out there. So stay curious. The next big discovery might be a dwarf planet with an underground ocean, a comet carrying alien chemistry, or even that elusive planet 9 lurking in the dark. Whether you're a backyard stargazer tracking distant worlds or just someone who gazes up at the night sky, remember, the solar system's story isn't finished. It's still being written, one icy fragment at a time, at the edge of everything we know.